Hi everyone. So I'm going to talk about a new way of thinking about execution sharding, and at the moment, let's think about why are we talking about execution sharding? What is it? Why do we need it? So right now, if you think about Ethereum, it has a very client-server design to it, and that's the problem with blockchain in general. And the end state, it's been very well recognized by everybody that what we need is a distributed computing end state. And this is all about computation running in optimized environment, best suited environments, and basically a more modular design. Now, what you have at the moment is that in this current monolithic state is that the libraries that your dApp is exposed to, or you're constrained to the libraries that exist on the network which you are built. Now, what we're thinking about is, we're seeing a lot of breakthrough with co-processors, but the co-processors by themselves will not give Web3 that breakout moment, that end state that we're looking for. Essentially, what we need is some type of orchestration between different environments. So what we're talking about is, when we talk about execution sharding, it's not just about one shard, but running multiple shards and gathering all the results together, a bit like how you have microservices in cloud. So it's a case of running things in these types of different environments, like AWS Lambda. Now, this last point is very important. It doesn't make too much sense on this page, and it's to do with the EVM and acting as a glue. So I'll move to the next page, which goes into more detail on this. So in a blog post in September, Vitalik basically discussed this approach to Web3 around distributed computing called glue and coprocessor. Now, in this blog, he talks about this central glue component having high level of generality and essentially shuttling data between different one or more coprocessors. And these coprocessors have low generality and are focused on specialized compute depending on what kind of functionality you're trying to achieve. Now, when we think about this design, the way we focus specifically on the glue component because the coprocessors, lots of people are working on that. They're just environments at the end of the day. But the glue component, how do you achieve this? How do you achieve this orchestration between different coprocessors? Now, in his blog post, he talks about the EVM being this glue component, but the EVM itself being, run on, on chain, it's constrained by the fact that it's expensive, slow, and you're constrained by what you can do within a smart contract. So the idea of having the glue as the EVM is quite difficult to believe, especially in Web3's current state. Maybe in the future, but right now or anytime in the next few years, that's just not possible. You're essentially talking about a smart contract pushing information to another network, that other network in a secure manner pushing information back to that smart contract, and doing that in an orchestrated way across multiple environments. It's just not possible from a cost perspective. Most things much simpler than this are costly enough already when it comes to Ethereum. So we need to go in search for better glue. Now, what we're proposing is another approach to this. And essentially, the way we're thinking about it is, if you push that glue from, instead of being in the EVM, which is basically something which is computation that runs across all nodes, if you push that onto the node itself, and specifically we're talking about the RPC node, the get client, and you use that to orchestrate between different environments, it can become a lot more efficient. And this is something which we're proposing. But the key to it, and the secret sauce, and I'll spend a bit of time on this, is the fact that when we talk about security and using network security, like what you do with smart contracts, our proposal, a key component of it is this on-chain token authority. Essentially, the application builder themselves deploys a smart contract on a confidential chain, somewhere where you can store a smart contract where the logic of the smart contract can be kept confidential. And the key reason for that is, within that smart contract, you would integrate a private key. which would then sign and attest for the computation that's being done. And the reason you would do that is you're forming a relationship between this on-chain token authority and essentially middleware, which is being secured by the token authority. So the token authority is extending its security onto the node. And the node's job is to act as the glue and orchestrate between different coprocessor environments. So by doing it in this way, essentially what you're doing is an application builder is solely responsible for their own security and extending it to the node. They can set it at as high of a level or as low as a level as they wish in an open framework design, whether you use private public key encryption or you use ZK proofs. It's your own design choice, and anything that happens in terms of if there's ever any kind of breakage, it's contained to the application themselves, because it would be a vulnerability in the way that they implemented this design. Now, essentially what we're talking about here is a controller-agent or a master-slave relationship, where essentially the node is doing exactly what it's told, and if it doesn't do what it's told and tries to do something different, and in any way behaves maliciously, this on-chain code is low smart contract just will not provide that end signature utilizing its private key to basically attest to the computation. And what you do by doing this is you're basically securing the whole process and the glue by the security that you have implemented yourself in this on-chain token authority. Now, putting this, just talking a bit more and talking about each of the components separately. So this on-chain token authority, I've covered some of it already, but essentially it would be deployed as a stateless smart contract. So we're talking instant, in terms of the speed and the cost of it, it would be minimal, and the latency would be close to nothing. You won't be waiting for a state change when this happens. As I mentioned, it's an open framework. You can set your own parameters, your own scheme, your own level of security yourself in this. And essentially, when it signs and attests to the compute which was conducted by the node in terms of the orchestration, that signature is basically then included as a parameter in the end transaction. So when the application receives it, the DApp receives it, it receives the result of the orchestration that was conducted by the node. It receives the signature from the token authority to attest that the computation was correct and you can trust the results. And what that means is the smart contract on Ethereum can take all of that, the results, the attestation, and say, okay, all the work's been done for me, I just need to focus on state change. Now that's basically the view of, you could say, Vitalik in terms of an end state, and anyone else who sees where we're going with blockchain right now. It's a case of we need to reduce the level of opcode that runs within the EVM, but we need to ensure that you can trust the security of everything that's executed. And we also need to be able to utilize functionality and also environments that are enhanced or optimized for specific types of functionality. And I'll go into a bit more detail on why would you do this? Why do you need more than one environment? I think most people know the answer to that already just by the number of L1s and L2s that we have. You kind of know that people want more than what exists just on Ethereum, and it's not necessarily always down to just cost and speed. Now, the node itself, how do you manage to orchestrate in this way at the node level? So essentially, the Get client already has on it a GraphQL engine. So essentially, our approach to this is to just add bespoke resolvers to the existing components of Ethereum. This is a very non-invasive implementation. The implementation I'm talking about does not involve creating a new network. It's not a new layer. There's no extra layer of consensus like a lot of other types of messaging protocols and things like that. We're talking about an Ethereum transaction going through an Ethereum node, going to an Ethereum smart contract. It's as simple as that. So essentially, by modifying the GraphQL engine, we can shuttle data off to other environments and bring that data back. As mentioned, this node is secured by the token authority, and it basically, after the execution of all the after all the orchestration, it gets all of that result and basically puts that into the parameter of the of the transaction, which calls the function of the smart contract. So doing this in a way, working within existing components within Ethereum, it results in basically a transaction following its existing path without any invasive new additions or any foreign entities being introduced. Now, what can you do with this? So we essentially are talking about moving a smart contract into a more modular component-centric design, where each component can be executed in a different environment. This basically also means that the EVM can just focus on state change, and the rest of the computation can run in more optimized environments. So the way you think about designing an application now would be different if you use this type of approach. And I'm sure most people understand or agree that the future of applications is cross-chain, and this is like, you could say, a shift in the first principles of how you think about making an application. Now let's think of an example of this and kind of put it into practice. So here what we've done is we've taken the Aave smart contract and just broken it down into different functions that exist within it. And by breaking it down into smaller functions, so this is just the typical logic of it, you can start thinking about this in a more of a component-centric or modular design. Now, if you look at what all of these different pieces do, you can think to yourself, okay, some of this could be run in a better environment. Maybe you run this one here as a stateless smart contract on Base, while the rest of it runs in on Ethereum. Maybe this one goes and runs on Optimism. Maybe this interest rate calculation can be a smart contract on Arbitrum. So what you can do is you can say, okay, let's shift this. Let's shift all of this to the node, where it's not necessarily really running on the node itself, but the node is orchestrating this and running it in different environments. Basically, every environment being a core processor, and this technology essentially allowing the node to orchestrate between them. Now, when you do that, what I've done here in terms of this design here is basically maybe that price, when you think about this component-centric design, what you end up with is the fact that each component can be separately upgradable as well and interchangeable. And they can be composable in the manner that they could be built by other people. So it basically moves Web3 towards, in Web2, you talk about NPM. So some people have called this the NPM of Web3. You can now utilize libraries that exist anywhere and use them within your application. So maybe you switch out the Aave Oracle and you use the one provided by Euler, right? You can just swap these around, change your price feeds, do it how you want. So we call this modularity, where you basically modularize your code base and run your logic in different environments where it's optimized. And essentially our design here just stitches the core processor results together and sends it off to the EVM for the state change at the end. Now, beyond this, it also opens up a wider design space. What it basically means, you can utilize anything anywhere, but then you can also have people who create, we call these kernels, by the way, these functions, where essentially it's just functionality built anywhere. But you can also have people who build specialized functions, specifically for application builders to consume. So instead of just your own code, what if it's someone else's code? So some of the people we've been working with recently are, and we have a track on the Hackathon as well, where you can actually integrate with the APIs and the on-chain functionality provided by some of these providers. So Elliptic, the KYT provider, if you want to integrate with them right now, as an application, you'd have to go and work with them. You'd have to form a relationship. This vendor, relationship that you have to form is even more, outdated than what you do in Web2, and we're meant to be moving forward. So in this way, you can have permissionless plug-and-play access to them, and you can basically integrate their kernel and allow compliance on your lending protocol. You can have KYT checks on the way in. That's an off-chain adding an open API adapter to GraphQL. This one here is just so Gitcoin passports, similar type protection, protecting against bots. There's over 1.5 million passports. More than 90 protocols use this. It's a smart contract on Optimism. Now your Ethereum smart contract can query that on Optimism, and the result and everything that's done will just feel local and native to the EVM at the end of it. So that's another one which you can just access. Compile and do something similar to Elliptic, whether it's different types of KYT, KYC, or regional restrictions. Maybe you create a lending protocol and you don't want people from the US to utilize that. So you can basically embed these functions which are built by specialized function providers who want to serve Web3. And a lot of this stuff is now coming together in terms of these Web2 and Web3 services. And this type of design allows this bridge to kind of like bridge the worlds together a lot more easier. The last example I give here is taint analysis. So if you're building a DeFi application, what you can do is you can take your full logic, your whole code base, run it on another chain as just like you could say like a ghost environment, a test environment. And essentially what you're doing is you're basically saying, I've created a version of my code so that I can put inputs in based on what someone's trying to do with my application. And if I get some kind of unexpected result on the other side, my actual smart contract will know, because they'll run in a test environment, and then my actual smart contract will know that this is quite a suspicious transaction that's happening. It's coming out, it's giving an unexpected outcome. So this is something that generally happens in terms of cybersecurity in Web 2, but we can bring this to Web 3. And essentially what we're talking about here is, and no other technology can do this, is you are talking about a real-time simulation being run on behalf of the application to determine if there's a threat to it. Now, from a DeFi perspective, this basically should help in terms of preventing hacks and reducing auditing costs and things like that, because essentially you've put in an extra layer of security here in a fully decentralized, permissionless manner using networks without introducing anything off-chain. This is a fully on-chain implementation. There's many other libraries of things you can use within Web3. You could, verifiable random functions is something which is not native in EVM, but it is in Aptos and Sui and other networks. Right now, if you're building something on Ethereum, like you want to mint NFTs and you need the randomization in terms of the minting, or you're making some kind of gambling game and you need the randomization, you would use something like a Chainlink Oracle. And these things would go off-chain, these trust assumptions associated with that. But with the NPM of Web3, you basically have access to libraries built by anyone, anywhere. So if you can, with an adapter, reach out to Sui and speak to an on-chain verifiable random function, you can do that on behalf of your Ethereum smart contract now. So the design space opens up quite a lot with execution sharding. It's an area which, a lot of people are focusing on how we can move to this distributed computing end state. This is just one implementation we've been researching for 2 years, and just recently productionized and released the private testnet just yesterday. So if anyone wants to play around or talk about this vision and what kind of new next generation of applications we can build with this, just feel free to catch me at any point. And feel free to follow us on Twitter and Discord as well. We may end up doing something eventually in terms of early joiners.
Hey, so what's the incentive for node operators to run this?
So essentially, the nodes are just RPC nodes. There's no incentive right now to run an RPC node, but you're basically talking about an application wanting specific RPC nodes to be in the cycle. So if an application builder already has to pay Infura Alchemy, we expect Infura Alchemy and these people just to run a cluster of these nodes. So these will be just in demand. Now, on top of that, there is a mechanism for basically those specialized kernels built by other people. They can charge for their application, for their function. And the expectation is the kernel protocol will take its percentage of that as revenue. So if Elliptic want to charge $1 per transaction, kernel protocol may take 5 cents to the dollar. And a component of that in the future could be paid to node providers. So RPC nodes right now are a bit of a cost center and a bit of a problem within the Ethereum stack because there's no incentive to run one. But this mechanism can actually create an incentive to run one based on genuine revenue which would be gas from the network.
How do you expect this modularity to affect the decentralization and consensus?
So the RPC node being pre-mempool, it again from a non-invasive perspective, it's doesn't impact the throughput, consensus, or anything to do with the underlying blockchain. All you're doing is choosing other environments which you want to orchestrate to bring in results, and all you're doing is bringing, parameters, data into the end smart contract. So you're not really impacting Ethereum in any way by doing it. All you're doing is choosing to utilize other environments to run your computation.
Okay, so all of the computation is done pre-mempool.
Exactly. Yes. And it's secured by this other on-chain token authority, and that's the beauty of it. If it's in the mempool, it's running across all the nodes. It's very expensive and slow. Running it at the node level, but securing the node is key to doing it. And in some ways, you could say we're talking about something which is designed very similar to EigenLayer, but without restaking, but using an on-chain token authority to secure the process rather than economic security. And that really opens up the design space because it means you don't have to pay for economic security, it's free. So you get open, free libraries being shared. It doesn't have to be a business to be shared. You can have a verifiable random function, and someone wants to use it, deploy it, make it, register it, make it available, someone else will use it.
Thank you.
One last question.
Hi, thank you. Could you say something more about the security aspect? So how can the node validate the distribution? So can I declare something and send the computation somewhere else, for instance?
Yeah.
So how difficult it is for the contract viewpoint to have a visibility outside of the chain?
Yeah, sure. Okay, so obviously we can go into more detail afterwards, and we leave it as an open framework from a security perspective, but certain things which we recommend and certain designs we've thought about is, so remember it's not the node securing, it's the token authority securing the node. So the node would share its runtime digest with the token authority, which basically says, hey, this is my code base, I'm legit, you can believe me. And then the token authority says, okay, go start running the computation then, do the orchestration. So that between all the orchestration, it continues to share its runtime digest, and only once all the results are in and the runtime digest is shared again at the last stage, will the token authority say, okay, I believe everything you've done, your code base is the one I have whitelisted, so I can believe your execution, thanks for everything, now I can attest and say everything is okay. Now, how the node has to obviously trust the information coming to it, and those are the GraphQL adapters. Whether you receive your information as a ZK proof or in any other way, or using some kind of messaging protocol, they have their own security for that component of the transfer. But from the node to the smart contract, that part is guaranteed by your token authority, which validates how the node itself behaves within the flow.
Great. So now we are going to first, thank you for Asim for giving us the introduce. We are going to the next talk of the morning.